Everyone, my name is Benjamin Lawson, and I'm presenting on the geomechanical characterization of mafic and ultramafic formations for TO2 mineralization as part of my final term presentation for the Geomech class in Virginia Tech. This presentation will try to understand the fundamental mineralogy and geochemistry of mafic ultramafic rocks, and then we'll move on to the interactions at the micro nanoscale with CO2, um, and then we'll look at the laboratory characterization of mechanical properties that are possible for CO2 in ultramafic rocks, and then we'll look at some of the field scale monitoring techniques and some of the governing equations that govern the mechanical properties at the field scale. And then we'll evaluate some case studies on the CAFEX and other CO2 mineralization projects. CO2 is a very harmful greenhouse gas, and it causes the greenhouse effect and global warming. Lan et al. Has clearly um, visualized how much CO2 in our atmosphere has been increasing for the past 45 years, and is showing that it's about 420 parts per million now. It is very essential that this CO2 amount doesn't go up, or we find a way to reduce this amount of CO2. Scientists have realized that the most effective way to reduce this amount of CO2 is to store it in subsurface underground formation. Now, in storing this CO2 in the subsurface underground formations, we've realized that CO2 undergoes four major types of trapping. The first is the stratigraphic trapping, which occurs because of the shape or the way the formation is oriented, such that the CO2 is injected into the subsurface and then it is sealed or it is trapped as a form of the stratigraphic orientation or topography of the formations. The next is the residual trapping, where CO2 is trapped in the pore spaces as a result of the residual CO2, or as a result of how much interplays between the interfacial tension of CO2 and water, and wettability and all that petro, pet- petrographical um, properties. The next is the solubility trapping, where CO2 is trapped in the formation water that is underground here as a result of the CO2 being dissolved in the water. And the last one is mineral trapping, where CO2 is stored as stable carbonates due to mineralization reactions between the CO2 and the host rock. Now, the IPCC special reports on CO2 capture and storage clearly states that mineral trapping is the most safest way of storing CO2, because its security, or the CO2 remains stored for a very um, large amount of years, about 10,000 years, and then the CO2 is really stored well, and there's no way of the CO2 coming up again into the atmosphere. So, mineral trapping, which we are looking at now, converts CO2 into solid carbonate, and it provides a near permanent immobilization of CO2. This also eliminates the risk of leakage of CO2 coming up, as um, this is very as the leakage risk is very prevalent in stratigraphic and structural trapping of CO2. Now, in mineral trapping, we found out that mafic and ultramafic rocks are the best hosts for mineralization of CO2 because of certain factors that we'll be discussing in the next slides. Now, since we are talking about mafic and ultramafic rocks, it is very essential to know how they are formed. In the earth crust and in the earth, mafic rocks are normally found on the oceanic crust, whilst ultramafic rocks are only found in the mantle. So if you find ultramafic rocks on the Earth's surface or in an outcrop, it has been brought up by a certain tectonic activity. Ultramafic rocks are very, very high or rich in iron, calcium, and magnesium, which are the divalent um, cations which are responsible for the mineralization. Mafic rocks, on the other hand, have a little bit lower amount of magnesium and iron, but have a little bit higher silica content as compared to ultramafic rocks. The continental crust is mostly felsic rocks, which is very high amount of silica. Now, due to how mafic and ultramafic rocks are formed, they are very crystalline in nature, and they are formed from an aggregate of minerals. You can see from here, gabbro, which is a mafic rock, is showing this high amount of crystallinity and mineral assemblage. You can see that these different kinds of um, minerals you are seeing here are joined together by mineral interlocking to form the rock. You can see that there are different kinds of minerals like olivine, which is here. You have serpentine, which is in the cracks and the micro cracks and voids in between those minerals. And then we have orthopyroxene and some pyroxenes, which all come together in the mineral assemblage, interlock and form these rocks. Why are mafic and ultramafic rocks ideal for mineralization? As I said earlier on, mafic and ultramafic rocks are rich in magnesium, calcium, and iron bearing silicates. And then these magnesium, iron, and calcium bearing silicates are the ones that are um, essential in converting your CO2 into stable carbonates. Key minerals in mafic and ultramafic rocks include olivine, pyroxene, um, plagioclase, serpentines, talcs, and chlorides. When these minerals come into contact with CO2, they produce new phases or secondary products like magnesite, which is magnesium carbonate, siderite, which is iron carbonate, and dolomite, which is magnesium calcium carbonate. And then these carbonate rocks or these new phases are very, very stable over time and are stored permanently in the rock. This figure is just showing you how um, mafic and ultramafic rocks differ in mineral composition, showing that olivine is very high in ultramafic rocks as compared to mafic rocks, and calcium rich phases are higher in mafic rocks as compared to ultramafic rocks. Okay, now the process of mineralization is not only a chemical process but it's also a geomechanical process. This is why. As the dissolution of primary minerals, as we have seen the talc, pyroxenes, olivines dissolve, calcium, magnesium, ions or cations are liberated from the surfaces or from the matrix. And this causes the matrix to lose some form of volume. Now, as the reaction proceeds and then the new secondary minerals are formed, that's the carbonate minerals are formed, there's precipitation of secondary carbonates and clays um, onto the rock matrix or the rock surfaces. Now, this process, dissolution and precipitation of um, primary minerals and precipitation of secondary minerals or carbonates, leads to volume changes, stress redistribution, grain contact modification, Now, these processes will also lead to degradation in strength, which is a geomechanical property. It will lead to stiffness reduction, which is related to strength. It will change our fracture toughness or the ability for the formation to resist, to propagate fractures. And it will also alter our permeability pathways. Understanding geomechanics is not optional because it is very, very, very important. It governs how much CO2 can be injected and how safely you can store CO2. This is because the mechanical degradation that we have discussed in the previous slide, it will reduce your fracture resistance. Yes, it can promote crack initiation because now your fracture resistance has reduced, meaning it is easier to promote crack initiation or to fracture your reservoir, which you might not want to do. And it is also easier or susceptible. The formation is now susceptible to fault slips. Now, as mineralization proceeds and carbonates and secondary phases are formed like clays, there's a risk of reduction in injectivity, which will inform engineers to increase your injection pressure, to increase the injection pressure in order to store more CO2 and access the further parts of the reservoir or formation. Now, this increasing pore pressure and this weakened rock, when coupled, can also raise a risk of induced seismicity. This is why geomechanics is very important when you are considering CO2 mineralization. Now, this effect is scaled from the ground, from the grain contact. That's the macro level, micro nano level, sorry. And then it moves on to the core scale, which is the macro level, just a few um, inches or a few centimeters away from the well bore or the injection um, bore or the injection well. Then it also scales up to the whole reservoir. So this geomechanical effect will not affect only grain contact or will not affect the nano or micro scale properties, but will also affect the whole reservoir. That is why it is very important to study the geomechanics or consider it whilst you are doing CO2 mineralization. On the next few slides, we'll be talking about the nano micro scale. Then we'll talk about core or laboratory characterization, which is the macro scale. Then we'll consider field and reservoir scales as well. Before we would even measure strength losses in a core or observe seismicity in a field, um, damage had already been accumulating at the grain contacts and interfaces at the micro scale. Before failure would even happen in the in the macro scale or the field scale, it would have already been accumulating in the nano micro scale. CO2 mineralization initiates at the mineral fluid interfaces where the CO2 dissolved, which is either maybe dissolved in the water or supercritical CO2 is comes in contact with the rock matrix itself. It also initiates at the mineral grain boundaries where CO2 can diffuse or get into these very small microfractures that are in between these mineral boundaries. Now, the rock property itself, or the rock properties of mafic and ultramafic rocks, comes from the grain contact mechanism, that's the interlocking, and how the grain to grain contacts is. It also comes from the interfacial bonding or the strength of the minerals that are interlocking. So as CO2 mineralization proceeds and dissolution occurs, these bonds are weakening and microfractures are being exploited by this CO2. What happens at the mineral fluid interface during CO2 exposure? Now, during CO2 exposure, I've already mentioned that the CO2 dissolves in the water to form carbonic acid. Now, this carbonic acid partially dissociates and gives us hydrogen, so hydrogen plus, which makes the medium acidic. Now, these H plus ions attack the host rock. When they attack the host rock, they release the divalent cations, leaving behind some silica and H2O. Yes, we can see here that olivine is being attacked by the H plus in the acidic medium to produce some magnesium 2 plus. The same here is seen for this um, dioxide, which is a plagioclase, and then this clinopyroxene also releasing calcium 2 plus and aluminum 3 plus. Now, after this dissolution happens, now the divalent cations are liberated and are mobile. Then this carbonic um, acid, which partially dissociated, has this ion present in the solution or in the aqueous phase. This then combines with the divalent cations that have been released to form the stable secondary phases, which are the which may be um, if it's in the case of calcium, you might have some calcite. If it's in the case of magnesium, you have magnesites. If it's in the case of iron, we have some siderites. Now, it is essential to know that these reactions are localized at high energy crystal surfaces, such that the activation energy or the energy that is needed to cause this dissolution and precipitation is lowered because the energy of the crystal surface are already high. And also it is localized at grain edges and pre-existing microcracks where this CO2 dissolved in water, that's the carbonic acid, has access. Now, as this CO2 mineralization is going on and it's in the right medium, all the um, properties are okay and suitable for secondary minerals to be forming. Sometimes these secondary minerals or carbonates, for that matter, can grow in confined spaces or pores. As this is ongoing, it can completely seal the pore, number one, or number two, it can generate tensile stresses. These tensile stresses being generated are as a result of the force or the pressure of crystallization. That's the crystallization pressure that is um, exerted on the rock matrix. Now, this figure is adapted from Zeng et al.'s paper, and then it's showing how the growth of secondary um, minerals can exert the crystallization force or the crystallization pressure onto the surrounding rock matrix. Now, this will essentially reduce the effective stress of the rock regime at that of the rock at that very instant there, and it will also reduce the fracture propagation property of the rock. Meaning, if I'm inducing more tensile strength and reducing the effective stresses, it means it is easier for me to drive microfractures even with a little um, pressure perturbation. Now, the process of precipitation dissolution is not homogeneous. It doesn't occur everywhere in the surface, in the rock matrix. As I've explained, it depends on a lot of factors like the whether they are microfractures, whether they are green surfaces, whether they are voids, the energy of the crystal faces, all that determines which places locally um, precipitation dissolution occurs. But then again, when you have a system like this, where precipitation dissolution is occurring actively, there might be a point in time where you can have this configuration where some parts of the system is undergoing rapid precipitation dissolution whilst other parts are still in contact like nothing happened. So if this occurs, there's an overburden pressure from the overlying rock formations. This pressure is translated into the contact here. Now, the dissolution of the rock matrix will affect or modify the grain contact, and it will modify the stiffness of the contact as well, such that now the stress at the contact is now equal to the force, that's the overburden force, and the area of the contact. So as this area even reduces further, the stresses increase. Now, this reduction in strength can also lead to um, or lower the load bearing capacity of the formation altogether, because you are now increasing the stresses on this very small areas as you are eating away the as you are eating away the rock matrix. So this may cause some form of subsidence, but it is not very common, but it's something that can happen, um, which happens very subtly. It's not very pronounced, and CO2 projects that have been piloted and scaled up have not really um, had issues of subsidence, but it's a very interesting um, concept that happens in at the grain or at the micro scale. So, as I've already mentioned, as CO2 mineralization is going on and these secondary phases are being formed, um, they can form in the micro cracks in the voids on the mineral surfaces, the grains, in between where as they grow, as this secondary carbonates grow, they exert this crystallization pressure, which induces tensile stresses in the surrounding rock matrix. As these tensile stresses increases, it causes cracks to form. Also, increasing injection pressure, pore pressure, can also cause microcracks to form. Now, how does this microcrack propagate or even go forward? Now, for a fracture to occur, a main fracture to occur, your fracture initiation should be higher than your K1C, that's your fracture intensity. So your K1C is the ability of your rock or formation to resist or to propagate fractures. Now your Ki, your fracture initiation, is given by your Y sigma root of pi A, where A is your crack, half of your crack length, your micro crack length. Sigma is your tensile stresses, and Y is your geometric correction factor, which is mostly 1 for rocks. So you can see that fracture initiation increases with increasing tensile stress and then increasing micro crack length. So as your micro crack lengths are increasing and your tensile stresses are also increasing, you are more susceptible to form cracks, or and these cracks coalesce to form um, fractures itself. So you can see here from um, this figure, micro cracks, as the tension forces increases, it causes a process zone to occur, and then in this process zone is where your crack lengths are being increased, and then your tensile stress is also causing the crack length to also still increase, and then it propagates, and then in the end you see a fracture being formed as a result of the micro cracks that had were there. So as mineralization increases and both your crack length or your macro crack length and your tension stresses are increasing, your reacted K1C would definitely be less than your intact K1C of the rock that has not been reacted, which means that it is easier to cause fractures in a mineralized sample as compared to the intact rock. Having spoken about all these micro nanoscale interactions that are happening, it is essential to know how these um, activities or these mechanisms are scaled to the core scale. So it is essential to know why we do the core scale or the macro scale. First of all, this macro scale or the core scale bridges the micro scale and the field behavior. It lets us know how this um, small mechanisms that or the mechanisms that happen in the nanoscale can affect the reservoir at a larger scale. It also provides quantitative mechanical properties which we can compare before and after CO2 exposure and know exactly how some of the rock properties are changing. Now, during core scale testing, engineers would normally look for parameters like Young's modulus, compressive stress, tensile strength, KIC, Poisson's ratio, etc. Now, these properties will serve as input for constitutive models. It will help us um, create some failure criteria. It will also help in reservoir scale simulations. Now, these tests which I've mentioned normally will follow an experimental framework. Um, the first step is to prep your sample. Now, in sample preps, you would normally use cylindrical cores or slab that are prepared from the intact rock. So, as you can see here, you have an ultramafic rock, which is maybe from a quarry or an outcrop somewhere, and then it's sent to a quarry machine, and then cores are cut out from or drilled out from this ultramafic rock sample. Then it's sent to a cutting machine where it is cut into various shapes for different tests. For example, for a BTS test, it is cut into this cylindrical slab. For a UCS test, you cut it into a cylindrical core like this, and then for a Q1C sample or the KIC sample for fracture toughness, it is prepared in a semicircular form with a notch this way. After the sample prep, then comes the reactor conditions, where the CO2 is exposed to, where the sample is exposed to the CO2 rich brines at elevated pressures and temperatures to simulate the subsurface condition. Now, this CO2 could be supercritical, it could be um, at subcritical pressures, which is to the discretion of the scientist or the researcher and the kind of conditions they are trying to simulate in the reservoir. So it's whole range of pressures and temperatures that are possible. Um, so normally this reactor would house the BTS samples or K1C or UCS samples in here, and then it is closed. A pressure gauge is attached to one of the um, threadings, the outlet here, and then the CO2 cylinder is connected, and then the CO2 is pumped into the vessel or the reactor, pressurized CO2, which is already having the samples in there with the CO2 rich um, solution. And this is the heating sample or the heating um, apparatus where after you are done setting up the reactor, you put in your reactor into the heater, which would maintain the reaction at a certain temperature. So after your reaction conditions and you set the reaction time to the time that you want, which may range from a few hours to days or months, then you recover your samples and then you go on to tests. Now, in mechanical testing, we could do before and after BTS, UCS, KIC, nano indentation, triaxial compression tests, acoustic emissions, etc. Um, you can see here this is a Anton power nano frame nano indentation device, and this is an example of a load frame which has the compression grips, which you could use for your UCS or BTS. And this is the schematic representation of an acoustic emission detection device. Now going on to the individual tests. First test is the uniaxial triaxial compression tests and its response to mineralization. So in the UCS tests, you use a core. Now this core is subjected to principal stresses, that is sigma 1, sigma 2, sigma 3. For the normal biaxial triaxial UCM compression test that we do, sigma 2 and 3 are the same, and it is provided by a confining pressure, which is represented in this triaxial cell here. So you load your sample in here into the triaxial cell, that's the core sample, and then your oil inlet would go around the sample, which is covered by a sleeve, a rubber sleeve, and then this hydraulic oil is pressurized and provides the K2, K3 confining pressure. Now on the ends of the core, we have the steel, hardened steel set, um, which is placed under the load frame, or if it is in a specialized triaxial cell apparatus, it also has hydraulic um, pressure that provides the K1 as well. Now, if we don't have K3 or if K3, Q2 are absent, then we have the uniaxial compressive strength test. But if you provide some confining, then we are in the triaxial regime. Now, as we are doing these compression tests, we are expecting the rock to fail. Now, there are two main failure criterions that are considered. That's the Moore-Coulomb failure criterion and the Hooke-Brown failure criterion. I'll explain both of them and then focus on the Moore-Coulomb failure criterion. So, in the Moore-Coulomb failure criterion, the shear stress, that's tau, is equal to the cohesion plus the normal stresses times tan of phi, where phi is the fracture angle, or the failure, the shear angle, friction angle. But in terms of principal stresses, the Moore-Coulomb failure criterion can be represented as this formula here. Talking about the Hooke-Brown failure criterion in terms of principal stresses, it can be represented as this equation. Now, the Hooke-Brown failure criterion is a little bit more hard because it's considered the failure of the rock as a non-linear relationship between principal stresses, whilst Moore-Coulomb considers the relationship between the principal stresses as more linear. We'll see an example here where data from a mineralized sample and an unmineralized sample, intact rock or geomorphic rock, compares to each other in terms of failure criterion, the more Coulomb failure. Now, in this example, a triaxial test is done on a mineralized sample, that's after, and then before mineralized sample, that's the intact rock. And we can see that given a confining, the same confining before and after, our K1 that caused the failure in the before sample, that's the before mineralization sample, was higher than the stress that caused the failure after mineralization. Now this is done for different confining stresses, and then the data is plotted on a graph. Now on this graph you can see which the blue one, which represents the before mineralization, and the orange which represents after mineralization. You can see that generally the rock will feel much at lower stresses after mineralization as compared to before mineralization. Now the points here are the actual test points, and the line is the Moore Coulomb failure criterion fit, which shows that the Moore Coulomb is actually the Moore Coulomb equation is actually able to predict the failure of the rock. You can see that after mineralization, the coercive forces reduce from 18 megapascal to 10.5 megapascal, which confirms all the discussion that we've had in the previous slides about um, the weakening of the rock and the reduction in the coercive forces in the rock minerals as mineralization proceeds. Next test is the Brazilian tensile test. Now, the Brazilian tensile test, which is measures the indirect tensile strength of the rock, um, was developed as an easier approach to measure the tensile strength, because the tensile strength of rocks are very hard to measure, and it involves um, getting the rock into specific shapes and having specialized equipment or frames in order to house this specialized cage rocks and to perform these tests. So as a result, scientists have developed an indirect way to measure the tensile strength of the rock. In Brazilian tensile strength tests, the rock slab is placed in a frame, which you can see here. And this frame is placed also in a load frame, like the Instrom load frame I showed in the previous slides. Now, the rock is then compressed, maybe at a constant displacement or constant strain, until the rock fails or a tensile failure occurs. So you can see here before before the test and after the test, the crack has formed. Now the peak load or the peak force that caused the fracture is used to calculate the tensile strength or the tensile stress of the rock. The tensile strength of the rock is given as 2p over pi dt, where p is the peak load, d is the diameter, and t is the thickness of the rock, which is usually half of the diameter. Now, tensile strength is highly sensitive to microcracks, as we have already seen. As the rock is undergoing this mineralization, and there are already some micro cracks in the rock, the tensile strength of the rock reduces such that as CO2, as the carbonates are forming in these pore spaces and micro cracks and voids, their crystallization pressure, which is induced on the um, rock, will cause the tensile um, forces to form in the rock. And if there are already micro cracks and the rock is weakened, the rock will um, develop more micro cracks even under very small stresses. Next test is the fracture toughness test. Fracture toughness can be measured in three modes. That's the mode 1, mode 2, mode 3. But the most common for fracture propagation is mode 1. In mode 1, we call it the opening mode, where the crack opens perpendicular to the plane of crack and tensile stress is perpendicular to the crack. Mode 2 would normally measure shear stress, where the crack slides in the plane of the crack and the shear stress is parallel to the crack front and perpendicular to the crack surface. In mode 3 is the tearing mode, where the crack tears parallel to the leading edge. So you have a leading edge and the crack is tearing parallel to it. Shear stress is parallel to the crack front. So the crack front and the shear stresses are in the same plane, are parallel to each other. Now going further into mode 2, mode 1. Mode 1 fracture toughness measures or quantifies the resistance of the rock to crack propagation. It uses a full on crack disc with a notch. Mode 1 fracture toughness. In mode 1 fracture toughness, the failure is due to the tension along the loading plane of the disc specimen. That is the diametral compression that leads to the tension tension failure. Mode 1 fracture toughness is measured or is calculated using this formula here that reads KIC equals to y prime times P max root pi a over 2RB, where the parameters or the variables are explained here, beta and y prime. Now the P max is the maximum load that causes the failure. Now mineralized samples would exhibit lower fracture toughness, which means that there's less energy that is required for unstable crack to go. From the BTS, we can infer what we call elastic modulus and the damage accumulation. This data here represents an ultramafic rock that has undergone an 8-week mineralization, and the BTS has been measured as a stress strain has been conducted, and Young's modulus has been calculated from that. The blue curve represents the before mineralization, and then the red curve represents after mineralization. After calculating Young's modulus, which is the stress over strain for the elastic region, we can see that the Young's modulus decreased after CO2 exposure. Now, modulus reflects the distribution of internal damage, and then this distribution can be quantified as damage accumulation, such that stiffness degradation, or that's the reduction in the modulus, precedes peak failure, which means that as there's internal damage, the macro cracks or the weakening of the sample itself will cause a degradation, and the sample will not be able to reach its peak failure as an unmineralized sample. The damage is quantified as D equals to 1 minus E over E naught, where E naught is the Young's modulus before mineralization and E is the Young's modulus after mineralization. Now, scientists have realized that often a reduction in Young's modulus would quantify damage. Now, from this data that you have here on the BTS, we're able to calculate the Young's modulus before and after, that is in the blue and the orange, for 3 other BTS samples. And then the damage D was calculated. This damage D ranges from 0 to 1. And a damage of 1 means that a very, very, very strong damage. And a damage of 0 means close to no damage. So after calculating the mean damage for these 3 BTS samples, we found out that the mean damage is around 0.57, which indicates a moderate to high distributed internal damage. Now, one design implication is that reduction in stiffness alters the stress distribution and deformation zones in the rock matrix, such that now the stress regimes will change. The stress regime that would have known to exist in the formation would change as a result of mineralization. Now, acoustic emissions can be is a test that can be coupled into a lot of other tests like doing BTS or UCS or even K1C. Acoustic emission tracks crack growth and crack initiation, and it can give an indication of chemical weakening as the samples which have lower resistance um, would initiate cracks earlier on or will have high crack times as the sample is undergoing failure or as the sample is being stressed under a test. And higher events will occur at very lower stresses and low times. And the reactor samples will show very early onset of acoustic emissions. So a before and after acoustic emission experiment would clearly show how a rock has changed before and after CO2 mineralization. And this will give scientists a clear indication of where cracks are formed, when cracks are being formed, and how much cracks are being formed as a respect of in respect to time and count. So in acoustic emission, the acoustic emission devices, that's a device that operates on the piezoelectricity, are connected to the samples, connected to a preamp and then to a collection system. As the sample is undergoing stresses, these micro cracks generate energies or acoustic energies which are picked up by the sensors and then amplified by the preamplifiers and sent to the collection unit and displayed on the system for you to visualize. From Guan, this is a visualization of an acoustic emission monitoring system from Guangjiang's et al.'s paper. The next test we can perform is the nanoindentation test. Nanoindentation test quantifies mechanical properties at the mineral and grain boundary scale. Nanoindentation is very useful because it can calculate a lot of properties, and it really doesn't need any special sample preparation. It also resolves the spatial heterogeneity because it can be performed on different spots on the core or on the sample that certain tests are not able to capture. Nano indentation is very simple, and what is done is that you have an indenter which has a certain shape. So depending on the shape of the indenter, a machine is used to apply a force. The force makes a dent into your sample surface. Depending on the height of the dent or the depth at which the dent goes in and the apply force and how much of the damage is recovered after the indenter is removed or after the load is relieved, you get a displacement curve. That's a load versus displacement curve. From this load and displacement curve, you can calculate so many things. We can calculate the hardness, which is giving us the load over the area which is the function of the HC, that's the height of the cone. We can also calculate the Young's modulus, which is a function of the slope, the area, and the area. Now, depending on the kind of indenter, we can calculate the fracture toughness when you use a cube corner indenter. You can calculate complex modulus, a lot of other complex modulus when you use the flat indenter. The conical spherical indenter can give you an idea of scratch resistance. The ball indenter is used to calculate stress strain, and the Berkovich indenter, which is here, is used to calculate Young's modulus and hardness of the rock. Now, one other test that you can also do at the core scale is the micro CT. Micro CT can help us to detect changes in pore geometry and size. It can help us to infer connectivity changes due to mineralization. It can also help us to detect how changes in porosity, that's the pore space, can affect permeability. Now, the only challenge with micro-CT is that it is based on segmentation, which is very subjective, and it depends on the user or the scientist who is doing this segmentation. Now, Carlo et al. Demonstrates how segmentation is done, where she has segmented the core itself, and then these are connected spaces in blue. That's the connected pores. This is how the pore connectivity, and this is the map of permeability or the pore connection, and then the curl or the vector space, how fluid would flow if it's flooded from this side of the core and allowed to drain on this side of the core. This picture is also just showing us how pore connectivities or pore network thickness can be mapped using micro-CT. Using the using the porosity that we get from micro-CT, we can calculate the permeability or infer permeability from the Cousin-Kalmar equation, which has been done here using an actual porosity data from a mineralization test that was done in the lab. You can see that from the blue line, which is the Cousin-Kalmar fit, the mineralization, the before mineralization samples, that's the untreated samples, experience or have higher porosities and therefore higher permeabilities as compared to the post mineralization, which have lower porosities and lower permeabilities on the scale of 10 to the power negative 17 meters squared, which shows that permeability scales proportionally or is directly proportional to porosity. So an increase in porosity would infer an increase in permeability and vice versa. At the core scale, we can see that CO2 mineralization reduces your tensile strength and K1C. Elastic, elastic stiffness degrades before microscopic failure occurs, and damage accumulates progressively at the core scale. Now, it is important to measure core scale properties because core scale properties define field scale model inputs. Laboratory results constrain safe injection pressures and inform a safe injection procedure, and mechanical evolution must be included in long-term design. As full scale geomechanical monitoring matters because when you inject CO2, you form a CO2 plume. The CO2 migrates, mineralization is occurring. Now, there might be points where the CO2 would migrate to joints that connect two different rock formations, and CO2 may leak. Also, the increase in the pore pressure could cause um, surface uplift, which should be monitored. Now, if the CO2 mineralization occurs and there's overpressure, it could induce microseismicity. Now, the injection of this CO2 also can induce thermal stresses due to the changes in reservoir temperature and the injected CO2 temperature, which needs to be monitored as well. Now, the CO2 mineralization and the changes in um, rock stress regime can alter or can um, um, disturb faults that are closer to the injection site. When these faults are disturbed, you can have microseismic events occurring. And these microseismic events can even escalate to very big earthquakes or induced earthquakes, which seismic monitoring can give us an idea of what is happening in the subsurface when it comes to um, microseismicity. The first thing scientists do or engineers do is to build an in situ stress model. In this model, what scientists are interested in is the vertical stress, maximum horizontal stress, minimum horizontal stress, and pore pressure trends. These stresses will help scientists or the engineers to actually know their injection procedure and how to inject into the reservoir. The vertical stress is normally given as the rho GZ, where it is calculated based on the lithostatic gradient or the overburden. Scientists then also would want to monitor deformation. In deformation monitoring, they use INSAR, which is the Informetric Synthetic Aperture Radar, which detects uplifts in subsidence that's linked to pressure changes in the subsurface. Also, GPS and UVA constrain horizontal and vertical displacement and can help in detecting changes in the surface topology or topography. Deformation patterns reflect fracture opening and pressurized zones. Um, so when these deformation patterns are picked up by the INSAR, it can tell us exactly what is happening in the subsurface, whether there's some fracturing occurring or there are pressurized zones. And then the VSP, that's the vertical seismic profiling, can also help us detect unexpected fracture deformations. The third field technique, which is the microseismic monitoring, um, is designed to detect small magnitude fractures and fault slip events. So the microseismic monitors that are put on the surface would help us detect if there's any changes in the fault regime, if small magnitude fractures are causing slips. And this gives us an indication of early warning instability, enables engineers to adaptively monitor pressure management when they use 4D seismic, and it tells them how pressures are changing over time. Now, the governing equation, which you've already seen, is the Moore Coulomb um, failure criterion. Now, injection pressure raises the pore pressure and reduces the effective stress. So, at lower effective stresses, there's more promotion of fracture, opening, and slip, which means that even at the moderate pressure changes, when the Moore Coulomb failure curves or the failure envelope has reduced or shifted to the left, at moderate pressure changes, the formation can be destabilized, and then the critically stressed fractures can also destabilize. Chemical weakening, which also causes the weakening in the cohesion, can further reduce this stability margin. Now, there's a minimum pore pressure, PSC, that is can cause that is used to determine what minimum pore pressure will cause the shear failure, which is determined from the maximum shear stress, here, the friction coefficient, and the mean normal stress. Changes in temperature can also cause thermal stress, as we've already seen. And because the CO2 injected is normally colder than the formation, the cooling can induce stresses and can also cause some fraction conditions locally near the wellbore. Now, the thermal stress is given by the E, that's the Young's modulus, times the tensile stress times the change in temperature, all divided by 1 minus Poisson's ratio. That's the change in the thermal stress. It's documented that a cooling of about 44 degrees combined with elastic properties, that's changing elastic properties, can give thermal stress reduction to about 10 megapascals, which means that we've reduced the effective stresses in the rock to about 10 megapascal, which is very concerning. We can estimate the change in the stress state due to thermal effects using the Poisson's ratio, which I've already explained here, coefficient of thermal expansivity, and thermal and temperature change. Given all that we've learned, we will solve a very simple problem. You are designing a pilot CO2 injection test in a fractured basalt formation that is 2 kilometers in depth. The rock density is approximately 2400 kilograms per meter cube, and the current pore pressure is hydrostatic at 10 megapascal. The original stress data suggests minimum horizontal stress is about 70% of the vertical stress. To avoid creating new tensile fractures, hydraulic fraction, you adopt a conservative criterion that tensile failure begins when the injection pressure meets the minimum horizontal stress, which is a very, very safe and it's a very conventional assumption that is made in field scale applications. Now, the first question is, what is the vertical stress at 2 kilometers depth? What is the minimum horizontal stress? What is the maximum allowable injection pressure to avoid tensile fracture? And how much pressure increase above the hydrostatic pressure is available before reaching the tensile failure? Now, this is a very simple example, and using the equations that we've learned in the previous slides, we'll be able to solve them. The answers are here for you to refer. That simple exercise will cool off by looking at two case studies. One is the car fix in Iceland, where CO2 was stored in a basalt formation, a fractured basalt formation, at a depth of 400 to 800 meters deep. The injection started in 2012 and ended about in 2014, and mineralization was achieved in those 2 years. About 95% of the injected CO2 was converted into solid carbonate minerals. Some of the geomechanical challenges that we faced were injection into the fractured dominated permeability network meant that the permeability was going to be reducing over time, right? Yeah. Risks of fracture clogging due to rapid carbonate precipitation was one of the challenges that we face. The reduction of injectivity due to declining um, pore space and reduction in permeability also was a geomechanical challenge. And the pressure buildup could promote fracture opening or shear slip if unmanaged, because um, the engineers were increasing their injection pressure as injectivity was reducing. There were also some microseismic events that were detected that were not so concerning, but they were very significant. Some of the remediation strategies that were put in place were to continuously monitor pressure, seismicity, and geochemistry using monitoring wells. The injection pressure was carefully controlled below tensile strength thresholds so that it doesn't exceed the fracture pressure, the fracture gradient, so that more fractures are not um, created that would lead to the seismicity. The next case study is the Walula Basalt project, which was in the United States. It started in 2013 and ended in 2014. The CO2 was injected in supercritical, and about 60% of the injected CO2 was mineralized in the 2 years. That's from 2013 to 2014. The CO2 was stored in these interflow zones, and mineralization occurred preferentially in the high permeability zones or high porosity zones. Some of the geomechanical challenges were pressure buildup within the lateral extensive interflow zones. So there was so much pressure buildup, and then this progressively reduced injectivity as well. This reduction in injectivity also caused fracture sealing, which is a good thing, but it means that you are the amount of the reach of the CO2 was reduced, because if the fractures are being sealed, the CO2 is not able to go outside a certain radius or outside the sealed zones. The remediation that were applied was to inject below the fracture thresholds here, and then scientists also monitored seismicity. They monitored the pressures and other properties using monitoring wells as well, and then they monitored the subsurface um, deformations and the surface deformations using um, GIS data, the mapping and the INSA. So also high CO2 to water ratio was used so that the mineralization is distributed more spatially, so that it can reach far further extends into the reservoir as time goes. So here are some of the references I used in this lecture, and thank you so much for listening.